Okay. See, once we have found out all these details, L, M, and the length and all of the pins for each of the elements, now let us write the element stiffness matrix for all the three elements now, because finally we need to find out the, you can say, global stiffness matrix. See here, now first let me write element stiffness matrix. See, in the last class I have already told you, in the general the element stiffness matrix is written as AE EE upon LE into bracket L LM LM M square. Here it is all minus L minus LM minus LM minus M square. Here also minus L minus M minus LM minus LM minus M square, and again here it is positive, that is LM and M square. This is how we need to write for each and every element. So obviously first let me take for the first element where the direction cosines are 1 and 0. So when I consider this, I will consider this as K1 for element number 1. Area is given 1500 millimeter square, and 2 into 10 raised to 5 is going to be my, you can say, Young's modulus, and the length of the element is 0. So therefore, look at this here. If you, for your convenience, you can write this as L and M. It is this one. So L square is also 1, LM is 0, M square is also L square will come 0.5. If it is taken this, it comes out to be 0.5. M square also comes out to be 0.5, but LM comes out to be minus 0.5 because this is negative and this is positive. So therefore, if you multiply both of them, it is coming minus 0.5. So therefore, the entries are, this is 0.5, minus 0.5, minus 0.5, and 0.5, minus 0.5, 0.5, 0.5, minus 0.5, minus 0.5, minus, this is going to be plus 0.5, this is plus 0.5, minus 0.5, this is 0.5, minus 0.5, this is going to be Yes, minus 0.5 and 0.5. This is what you are going to get this. Once you have substituted all this, you will be getting that. Then you simplify this, all this, and if you take the remaining part inside, this is going to be 10 raised to 5, and it comes out to be 3.535. This one. Minus 3.535, minus 3.535, 3.535, minus 3.535, 3.535. This is 3.535 minus 3.535. If you just take the same thing here, minus 3.535, 3. This is all the same, like this is all going to repeat. Very simple to write down all these things. See, if you look at this second element, connectivity, so see here, you have what you have taken is 2 and 3. You have taken, this is going to be Q3, Q4. This is going to be Q5, Q6. This is the second element, what you have taken. So obviously the order is 3, 4, 5, 6. So you have to take 3, 4, 5, 6. 3, 4, 5, 6. This is very useful for our global assembly. That the connectivity is going to be very, very important for us. Similarly, if you look at this, K3 is very, very simple. Everything is remaining same. So therefore, I will not waste my time. Directly I will write this is going to be 3.535. Everything comes out to be positive here. 3.535, 3.55. See here all the 4 elements are going to be positive. So therefore all these remaining 4 elements are going to be negative only. Yes, this is going to be the connectivity. See, if you want to write the connectivity for this, look at this. This is going to be 1 and this is going to be 3. So therefore, this is Q5 and Q6. And this is going to be Q1 and Q2. So 1, 2, 5, 6. 1, 2, 5, 6 is going to be the connectivity for this particular element. So therefore, that is need to be written here. 1, 2, 5, 6. 1, 2, 5, 6. Okay. So once you have written the 3 element stiffness matrix for each one of them, now directly let us go for the global stiffness matrix. Okay. See, to save our time, what I will do is, I will directly consider the FEM equation KQ is equal to F. Okay, since there are totally 6 degrees of freedom, Q1 to Q6, obviously my global size is going to be 6 by 6, 6 by 1, and this is going to be 6 by 1. That means there are totally 6 nodal displacements, 6 forces at 6 degrees of freedom, as well as the global stiffness matrix size is going to be of 6 by 6. So let me write 10 raised to 5. Okay. Let us take K11, K12, K13, like that. If you take, look at this, there is going to be 3.75, which is already there here, 1, this is there here, 1, 1, and one more here, you can see here, there is one more 1, 1 here. So they get added, 3.535 and 3.75, altogether it comes out to be 7.285. See, this is the first assembly when you are starting with. This is going to be the first, like let us say 1, if I write 2, 3, 4, 5 and 6. Okay, this is going to be my size. Later on I will complete that. Then similarly, if you go for the second one, 3.535, 3.535, 3.535, and this as usual comes 3.3. This is again interesting. This is going to be 1 and 3. You can see here 1, 2, 3, 4, 5, 6. If I take this element is 1, 3. 1, 3 you see here. What is this 1, 3? If you look at this 1, 3, there is a minus 3.75 is here, and there is one more 1, 3. Is it there? Do we have one more 1, 3 here? No. So there is no one more. So therefore, 3 and 1. This if I take here, this is going to be my minus 3.75. Okay. So therefore, that is the reason I have written it as minus 3.75. Okay. Then there are no other entries here. This will come 0, 3.535 minus 3.535. This is the sixth entry. Whereas here if you come, these are 0, 0, 0, zeros, minus 3.535, minus 3.535. Third, it is again same, similar to 1, 3, 3, 1. They are symmetrical. They are coming same, 0. 7.285 is again coming here also, minus 3.535, minus 3.535, plus 3.535. Yes, this will come. Fourth, it is going to be 0, 0 because there is no 4, 1 or 1, 4. It is not there, even though it is there. 1, 4 and 4, 1. Both are zeros here. See, 1, 4 and 4, 1. They are going to be zeros. So there is no entry there. Similarly, 2, 4 and 2, 0. 4, 2. Both are again going to be 0. This is entered. Minus 3.535. 3.535. Okay. This is 3.535 minus 3.535. Then here comes minus 3.535 minus 3.535 minus 3.535 3.535. Yes, if you look at this 5, 5, there are two 5, 5s. You can see here. There is one 5, 5 here, and there is one more 5, 5 here. So once again, they get added, and the same thing you will get now. This will be 7. minus 5.3, 3.535, 7.071, 0, 3.535, 0, 7.071. This is the remaining matrix 3 by 3 which is remaining. The nodal displacements are Q3, Q5, Q6 are going to remain, and the forces are 0, 0, minus 150 into 10 raised to 3. This will be the final leftover equation, and you have to solve by using any of the techniques like Gaussian elimination techniques or with the help of your calculator if it is possible. So please calculate Q3, Q5, Q6. After I have calculated, what I am getting is this comes out to be 0.2 mm, 0.1 mm, and this comes out to be 0.312 mm. See, this is how you are going to get the, you can say, nodal displacement, 3 nodal displacements. So therefore, the total global nodal displacement is going to be 0, 0, Q3 is going to be 0.2, Q4 is 0, and Q5 is 0.1, and Q6 is 0.312 transpose mm. Because it is a column matrix, it is a 6 by 1 column matrix. Though I have written it in a row form, with the help of the transpose, I can reduce it to a row matrix. So our objective is confirmed, that is, I have now got all the displacements now. Okay, once I got the displacements, my next step is to find out stresses in the members. Okay, what is the, how to find out the stresses in the member? Sigma E is given by E1 by E upon E, that is the element of this thing, minus L minus M, L and M, and this is going to be Q1, Q2, Q3, Q4. This is what you have to write this. So therefore, this Q1, Q2, Q3, Q4 are very much similar to the one what you have taken the connectivity for element stiffness matrix. The same thing need to be found out. For example, if I want to find out sigma 1, okay, what is this? 2 into 10 raised to 5 is going to be this, and the length is going to be 800. Yeah, L is going to be 1, so therefore it is minus 1, and other one is 0, then 1 and 0 here. Yes, here you know that it is going to be Q1, Q2, Q3, Q4, because the element connectivity says like that. See, these are all going to be 0, only the Q3 value is there, that is equal to 0.2. So we can calculate this now and directly find out the stress. So this stress comes out to be 50 Newton per millimeter square. It means, it is positive, means the member is under tension. There is a tensile stress is going to act on this. This member is under tension. That you have already seen that when I showed this, when this displacement has moved to this, obviously this length has been increased now. This is the increase in the length because this member is moving in the horizontal direction to the right. So obviously it is stretched. So the member is under tension. Now similarly, if I want the second member, it is E upon L2, and corresponding L and M and all that has to be taken. Now the most important part here is you have taken from here to here, so that is Q3, Q4, Q5 and Q6. This is the arrangement you have taken. So therefore this will become 2 into 10 to 5 upon, what is the length? 565.68. And what are the, you can say, these values? I think you have taken minus 0.787 is coming, so therefore this will become now positive now, because minus of minus will become positive. This was positive, so therefore this will become negative. This was originally negative only. So therefore L is minus 0.707 and this is 0.707. It will be there. And Q3 just now you have calculated. What is the value of Q3? 0.2. Q4 is 0. Q5 is 0.1 and minus 0.312. So if you look at this, the stress comes out to be, for the second element, it is minus 53 Newton per minute square. So that means this member is under compression. See, because the load is coming down, though the node 2 is moving forward, but the displacement due to node 3 is coming downward, this second member is under compression like this. Okay. So this is how you can find out the second stress. Similarly, I can find out the stresses in the third member, sigma 3. Sigma 3 is going to be, Young's modulus is same, then this is L3, it's L minus M, Lm, yes. Here comes, interesting, 1 and 3 are connected, so there